In this video, we're going to discuss function graphing in more detail. So we talked a little bit about graphing in the last section. Ultimately, we just graphed by plotting points. And I want you to keep in mind that that is always an option. You can just choose X values, find associated Y values, graph the ordered pairs, connect the dots. That's how you typically learn to graph in the beginning. However, in a lot of cases, that's not going to be the most efficient way to graph. One thing we're going to want to do as we look at functions more is to get to the point where we can categorize functions based on similarities between different types of functions. So as we categorize the actual equations, it's also nice to be able to categorize the graphs. So based on the type of function we're seeing, we can expect specific types of graphs. So rather than having to look at every function as a brand new function that we've never seen before, it's nice to be able to take certain types of functions and generalize the kinds of things we know to expect just based on the type of function we have. So when we graph, what we're going to do is relate the particular type of function we have to what we call an elementary function or a parent function. Think of the elementary or parent function as the most basic function we have that represents a particular function type or particular function category. So what we're looking at are similarities between different types of functions in terms of specifically the types of operations that we see in the function. For example, these three functions, g of x is x squared minus 4, h of x is x minus 4 quantity squared, and then k of x is negative 4x squared. So these are all three different functions. All three of them would have different graphs, but these all have a similar exponent of 2. They're similar because they all have a highest exponent of 2. So what this means is that all of these functions and then all of their graphs are actual just variations of the function f of x equals x squared. This is going to be a particular elementary function. It's a parent function. It's the most basic function that has an exponent of 2 attached to it. So if we were to take this particular function, specifically take its graph, and then make some slight changes to it, take some variations of this, that's going to allow us to generate these three different functions. So notice the first one, the only change between x squared and this actual function is the fact that we've taken x squared and subtracted 4 from it. Subtracting 4 from it represents a specific type of change to its graph. Same kind of thing here. We're also subtracting 4, but notice we're subtracting it in a different way. Here we're subtracting it from the whole x squared, whereas here we're subtracting directly from x, and then we're squaring it. So this is a different type of change to the graph. Here we're multiplying by a negative 4. So all of these different operations are different types of what we call transformations to our function. So they're going to take this function x squared and take its graph, and they're going to apply a specific change to it. But if we were to graph all of these functions, say we just graphed them by plotting points or put them into the graphing calculator, what we're going to find is that they all have the same shape. The shape they have is based on the shape that this function's graph has. So by starting with something like this, starting with f of x equals x squared, a super basic function that just models a general type of function, we can then take that graph and make slight changes in order to generate pretty much any functional graph we want that's related to this x squared graph. So where we're going to start is with our list of elementary functions. This is going to be one of them. We're going to have several others. So depending on what our function looks like, it's going to be a variation of a different type of elementary function. You are going to have all of these memorized. So what sort of things do you need to be able to do? Well, if you see the graph, you need to know what type of function it relates to. If you see the function, you need to have a sense of what the shape of the graph is going to be interchangeably. So our first simple function is called the identity function. Identity just means essentially nothing is changing. So the identity function is going to be f of x is equal to x. So what this function rule is saying is that if we take x, plug in an input, then the output exactly matches the input. In other words, we don't have to do anything to an input to get an output. All of the x and y values are going to be the same. So for instance, if we plugged in 0, we'd get out 0. If we plugged in 1, we'd get out 1. And that's going to be the case for all x values that we get. The y value is the same as the associated x value. So if you were to graph a function like that, that's actually going to be a perfect 45-degree diagonal that goes through the origin. That's what the set of ordered pairs looks like when all the x and y coordinates are going to be the same. We can also see this on the graphing calculator. So if we were to graph this function, f of x, remember that's the same thing as y. So where we see the y, that's the f of x if we're going to try to type in a function to graph. So our rule is just f of x is equal to x. We don't actually change anything. So f of x is equal to x or y is equal to x. And if we graph it, this is going to be the graph we get. Now, this is a perfect 45-degree diagonal where this one looks like it's maybe a little bit less than 45 degrees. Remember, that's because of the zoom setting. In this case, let's go back to zoom standard. I'm zoomed way out from something we did last video. There we go. There's zoom standard, so this is probably what you see. And again, it's slightly warped from this particular perfect 45-degree shape. That's because the y scale and the x scale are different. So if you go to zoom and zoom square, which is option 5 instead, then you get that nice pretty 45-degree diagonal because the x and the y scale are going to be the same. And you can also see the values in the table. So second and graph is going to give you the table. Notice for all the x values you get, regardless of whether they're positive or negative, the y value is going to match. So that's going to be the hallmark of the identity function. So how would you use the identity function? What does this really mean? In terms of it being an elementary function, a most basic function, it's going to be the most basic function that would give you a linear graph. So any variations you take of this, what do we mean by variations? Well, if you were to multiply this by a number, add or subtract a number, anything like that, it's going to give you another graph that's shaped like this graph in the sense that it's a diagonal line. But adding on, subtracting, multiplying, any of those kinds of things are going to take this basic line and they're going to change it in a specific way, just depending on the type of operation that we're applying to the function. But this is going to be the parent function for all of the linear functions we get, all the linear functions that graph as a line. So that's how we're going to use it. Anytime we see a function that is a variation of this, we know this is the graph we'd start with, and then based on the additional numbers we see in the function, that tells us we have some specific changes that we would apply to that most basic graph. Now the one we just looked at, the one that's common between these three functions, is going to be the square function, which is f of x is equal to x squared. So this rule tells us plug in your input and square it. So squaring is specific in terms of what it does to numbers. We square any number, we always get a non-negative output. So the lowest output you can get from the squaring function is going to be 0. You square 0, you get 0. But if you square any positive or negative numbers, the outputs are always going to be positive. That gives this graph a very specific shape. The whole graph, notice it's above the x-axis. In this case, because all of the outputs we get are going to be positive numbers, regardless of what we plug in. And it's going to be a U-shaped graph. The reason it's U-shaped is because of how the values increase. So squaring, the higher the input is we plug in, the faster it gets bigger. So plugging something in and then squaring it means the output gets larger, faster than the outputs increase if we're talking about something like the identity function. So if we were to graph these three functions, we know they're going to be U-shaped graphs because they come from this squaring function. So each one of those three graphs would look different, but they would all be U-shaped graphs because they're variations of this squaring function graph. Okay, we've got 4 more. The cubing function. So cubing means raising to the 3rd power. Cubing is different from squaring in terms of the types of outputs we can get. So if we square a number, the output's always going to be positive. If we cube a number, that's not always going to be the case. So if we cube a positive number, think positive times positive times positive. That's what cubing means. If we cube a positive number, the output's going to be positive. If we cube a negative number instead, the output is going to be negative. You can verify this with your graphing calculator. So say you were to take, for instance, -1 and cube it. Now remember, we talked a little bit about exponents applied to negatives last video. You have to make sure you put parentheses around the negative. Otherwise, your calculator doesn't apply the exponent to both the number and the sign. It'll only apply it to the number right next to it, and then it'll just make the number positive. So we want to put -1 in parentheses, and then we use the up arrow for exponent, and then we're cubing. So notice we get a -1. So if we were to take 1 and cube it, we get +1. If we take -1 and cube it, we get a -1. So the cube function differs from the squaring function in two ways. Number one, the signs can vary. So cube a positive, get a positive, cube a negative, get a negative. That's one difference. The other difference is things that are cubed get faster or get larger faster than things that are squared. So if we're squaring, numbers get fast at a particular, or numbers get large at a particular rate. If we're cubing, they get larger faster. So we can see this by just taking a few inputs and cubing versus squaring. So if we were to take 1 and square it, we get 1. Take 1 and cube it, we also get 1. So that's not going to change. That's going to be consistent for both of those functions. Now what about a 2? If we take 2 and square it, we get a 4. If we take 2 and cube it, we get an 8. So on the squaring graph, we would have the ordered pair 2, 4. On the cubing graph, we have the ordered pair 2, 8. If we were to take 3 squared would give us 9. 3 cubed would give us 27. So the variation here shows us that cubing something is going to make the numbers larger a lot faster than squaring. That's going to be the same for higher exponents as well. The higher the exponent, the faster the numbers get bigger or smaller if we're talking about numbers that can go negative as well. So we end up with a little graph that looks kind of like a swimmer. I think it looks kind of like a swimmer right there. So that's going to be our cubing function. So if we see a function that's a variation of this, that has something that's being cubed, the variable is being cubed, then we know the graph is going to have this shape. It's going to be some variation of this shape. So that's the highest exponent we're going to look at. Just keep in mind, the higher the exponent goes, the faster the numbers get larger. Now, if we can square something, we can also take a square root. Those are what we call inverse operations. So here's how something like that would look. If you were to take 3 and square it, you're going to get 9. The same statement, but using a square root, would be the square root of 9 is equal to 3. So think of a square root as what undoes a square. So if we square 3, we get 9. If we take the square root of 9, we get back to 3. So a square undoes a square root undoes a square. So they're going to have graphs that are similar in shape. The square root function graph and the square graph are related in a very specific way. If you look at the square graph, imagine turning it on its side so that it were oriented along the x-axis instead of the y-axis. If you were to keep only the upper branch, that's going to be the square root function. So there is a very specific relationship between these graphs. We're not going to explore that in too much detail, but suffice it to say they have a similar shape for a particular reason. Now, notice one thing here about the square root function. Notice it stops there at the origin. There's nothing to the left of that. That's because this particular function is undefined for any negative inputs. The lowest number you can plug into the square root function is going to be 0. If you try to plug in anything smaller than that, you're going to have a problem because we can't actually take the square root of any negative numbers. You can see this most easily from the table. So if we were to graph this function, let's do this. So we're taking the square root of x. So second square root, so second square gives you the square root, and we're graphing the square root of x. I'm going to hit graph just to verify that this is in fact the graph. Okay, there we go. Now let's look at the table. The table will give us these ordered pairs. So we plug in an x value, we take the square root, that gives us the corresponding y value. So second and graph takes us into the table. Okay, and you'll notice something sticks out like a sore thumb really quickly. Let's start here at 0. So 0, 0. If we plug in a 0, we get a 0 out. If we plug in a 1, we get a 1. Notice plugging in 2 or 3, those give us decimal numbers. That's because if we plug in a 2 or plug a 3, the output is what we call an irrational number. We can take the square root of 2, we can take the square root of 3, but suffice it to say, it's not going to give us a pretty number. So the ordered pairs that we choose to graph on something like this are going to be the ones that give us pretty outputs, if you want to think of it that way. So an output or an input of 1 is good. If we were to take an input of 4, take the square root, we get a 2. We take an input of 9, take the square root, we get a 3. The next one would be 16. So 1, 4, 9, 16, 25, 36, those are called perfect squares. Those are the numbers that you could plug into a square root and get an integer output from. But keep in mind, all the other numbers between those, as long as they're positive numbers, we also can take the square root of. We're just not going to get a really nice output. But we verified the shape. Here's what I want you to notice about this table though. We start there at 0, 0. We have a point at the origin. Okay. What happens if we look at negative inputs? Notice for -1, we get an error. It says error. In other words, the graphing calculator tried to plug in -1 and somehow it didn't work. Same thing for -2 and -3, -4, so on and so forth. All of these x values give us an error for the y value, because when your calculator tries to substitute in these values, it gets something that it can't actually graph. There are other ways to deal with something like the square root of -1, but it requires us getting into things that don't actually exist on our coordinate plane. So the way we would formalize something like that, recognizing that there are errors, is we would say that the domain of the square root function is 0 to infinity. So what that means is that if we look at the whole set of inputs for this particular function, we can take any input from 0 all the way up to positive infinity, anything we want, but we can't plug in anything that's less than 0. Any input less than 0 results in something that's undefined. So the domain of the square root function would only be from 0 to infinity. This is unique to this particular function. If you look at the other functions we have so far, what you'll notice is that they would continue forever and ever and ever across the coordinate plane. So the identity function, we have graph all the way from left to right. That means x values from -infinity to positive infinity. Same thing here, although the graph cuts off, keep in mind you're essentially branching out forever and ever, which means we would also cover the whole coordinate plane from left to right, from -infinity to infinity. Same thing with the cubing function. Again, imagine there are arrows there. So we're continuing diagonally, albeit it's pretty steep, but it's still diagonal in both directions forever and ever, all the way from -infinity to infinity. This graph specifically stops horizontally at 0. So it goes from 0 to positive infinity, but it stops and we don't get anything less than that. So that's a pretty unique graph. We aren't going to see anything much more unique than that, but that is one where we have to keep in mind it doesn't cover the whole coordinate plane, it only covers one specific section. Now we can also take a cube root. A cube root is like a square root, but square root is to square as cube root is to cube. So if we were to, for instance, take 2 and cube it, we get an 8. The cube root would undo the cube. Now, where do you get a cube root on your calculator? It is here, but it's not on one of the buttons that you can see. So the square root is right there above the square. You don't have a cube root because you don't have a cube button. Here's where you find it. You're going to go into the math menu, which is right below alpha. So hit math. And then in that first sub menu, if you scroll down to option 4, that's going to be a cube root. Option 5 also has a radical, but it has a little x in the window. That would be where you would get any other type of root. So a 4th root, a 5th root, something like that. Cube root is probably going to be as high as we need to go though. So option 4, I'm going to select that, hit enter, and that's going to give me my cube root. So if I take 2 and cube it and get an 8, then that means that taking the cube root of 8 would give me 2. So cube 2, we get an 8. Take the cube root of 8, and we get back to a 2. So you can see the relationship between the graphs even more clearly looking at the cube function and the cube root function. If you were to take this cube function, and technically what's happening is if you imagine that diagonal down the middle, if you were to reflect it across the diagonal, then this is going to be the graph that you get. So very similar shape, but it's just been reflected diagonally is essentially what's going on. And then our last graph we're going to look at is going to be the absolute value function graph. Absolute value means a couple different things depending on your perspective, but if in the simplest sense, the way you first learn absolute value is it takes everything and it makes it a non-negative number. So if we plug in a 0, we get a 0. You plug in a positive number, it gives you out a positive number. If you plug in a negative number, it just flips that number and it makes it positive. So where do you find absolute value on your calculator? You can also find this under the math menu. So math, if you go to num, which stands for numbers, 1 is ABS, which stands for absolute value. So if you highlight that, hit enter. It may say ABS. If you have a slightly older calculator, it may just say ABS with parentheses. Or if you have a newer calculator like mine, notice it gives you the bars. The bars are the absolute value bars. So you see those vertical bars? That means absolute value. So if, for instance, we were to take the absolute value of -2, that's going to give us an output of 2. So if we think of plugging in a -2 as an input, 2 would be the output we would get. So -2 is x, and the corresponding y value is going to be 2. So that would be -2, 2, and the absolute value of 2 would also be 2. That's going to give us a V-shaped graph. So I want you to make a careful distinction between the squaring function graph, which we call a parabola. This is a U-shaped graph. There's an actual curve to this graph as we go from ordered pair to ordered pair across the coordinate plane. The absolute value graph, these are actual straight lines. So if you were to imagine taking the identity function and leaving the right-hand side, but taking the left-hand side and then reflecting it, flipping it up, that gives you the absolute value graph. So this is truly a V-shaped graph. So again, I'm not really looking for artistic ability here, but drawing a graph with curve versus drawing a graph that has straight edges, there is a very distinct difference here, and we do need to be able to differentiate between the two. So although we haven't done it here, I strongly recommend either pause the video or maybe do this later. Go back and go through all of these functions, all of these basic functions. So the identity function, the square function, the cube function, square root, cube root, and absolute value. I want you to go through all of these and verify all of these ordered pairs that have been graphed. How can you do that? Well, in the first section, we looked at graphing point by point. In other words, just pick an x value, solve for a y value. Go through and pick some x values, solve for the y values, and make sure that you can, in fact, graph and reproduce these particular graphs. Another thing that you can do is you can graph them on your graphing calculator and then go to the table function. Again, the table function gives you all of those ordered pairs that have already been solved for. So verify that you can, in fact, get these particular graphs. Verify the shape based on the ordered pairs you get. Going through the actual procedure of doing that is going to help you to remember what these graphs look like, because you do need to have these memorized. So if you see, for instance, the cube function, you know it's going to be a graph shaped like this. If you see a graph shaped like this, you know it came from a cube function. So spend some time working with these, verifying all of these ordered pairs that we have graphed, and that's going to help you remember these graphs a little bit better. So anytime we see a graph that has one of these particular shapes, not only do we know that they have the same parent function, but we know that their actual equations are going to have the same operations. So they have the same parent function, which means we're looking at the same operation. Just like those first three equations, we didn't actually graph these functions, But if we were to graph them, they're all going to be variations of this graph. If we in fact have 3 graphs that look like this, then we also know that they came from 3 equations that looked similar. So what we want to talk about now is if we have one of those functions, for instance, one of those squared functions that has something else going on algebraically, has something multiplied, has something added, something like that, how do we know what to expect from the graph? Well, again, we know the shape. We know what the shape is going to be based on the operation we see. If there's a square, it's going to be a U-shaped graph. If there's a square root, it's going to look like this. If there's an absolute value, it's going to look like this. But how is it going to change? What are the variations going to be to get the actual graph we're interested in? So the variations from a parent function to an actual function are what we call transformations. So each of the individual things that we can do to a parent function to change it is what we call a transformation. So it transforms the equation, and it also transforms the graph of that equation based on the original parent function's graph. So a transformation is going to occur in 3 different ways. It can occur if we add a number, if we subtract a number, or if we multiply. Now notice I've left out division. We're not going to treat anything as division. We're going to treat a division as a multiplication. I'll explain more about that in just a minute. We can do individual operations. We can do a combination of these. But anytime we have one of these additional operations, adding a fixed number, subtracting a fixed number, multiplying your function by a fixed number, we know we have a particular type of transformation to our function and to its graph. So 2 things are going to be important when we're identifying what's happening to our graph. Number 1, we have to look at the type of operation. These are the types of operations we're going to see. The type of operation is going to give us the type of transformation. We also have to pay attention to the location of that particular operation, specifically inside of the function. So what do I mean by that? Well, if I go back to the first page, those 3 functions that we had, I want you to look at these first 2. Notice both of these featured a subtraction of 4. We had x squared, x squared, x squared. That was what these 3 functions had in common. These first 2 functions both have a subtracted 4. But notice the 4 is subtracted in a different way from these 2 functions. So for the first one, we took x squared as a whole unit and then subtracted 4 from x squared as a unit. Whereas here, we subtracted 4 directly from the variable, directly from x, and then we squared it. So we can kind of think of this subtraction as being outside of x squared, whereas this subtraction is inside of x squared. Whether it's outside or inside is going to make a difference in terms of what transformation we see in the graph. So they're both going to be the same type of transformation because they're both subtractions, but the location of each of those subtractions is going to give us a different variation of that particular type of transformation. So I've got summarized in this table all the different transformations we're going to see. I am going to give you this table for you to work off of. So you're just going to have to be able to identify what you see from your function. So if you see the function, what's going to happen to the graph? If you see the graph, well, what happened to the function? So the first type of transformation we have is a vertical shift. Shifting just means moving, sliding. So a vertical shift means sliding it up or sliding it down, taking the original parent function's graph, sliding it up or sliding it down. So this particular transformation is going to result from addition or subtraction, but specifically it's addition or subtraction onto the entire parent function. So attached to the whole parent function, not directly to x. So for example, if we were to look at that first set of functions, it's going to look like that. So notice that subtraction is outside of the parent function. If we were to think in terms of order of operations, we square first and then we subtract. So the subtraction is outside of the squared function. That's what this is going to look like. So in this case, we have addition or we have subtraction that's outside of the parent function if f of x represents our parent function. So if we're adding outside the function, that's going to shift us up. If we think of f of x as representing y values, then we're taking our y values and we're adding on a certain number to them, which is going to take all the y values and it's going to move them up that many units. So adding on a number outside our function is going to shift our parent function graph upward that many units. If we subtract instead, but it's outside of our function, that's going to shift us down that many units. So the first function we had right here, x squared minus 4, that would take the x squared graph and it would take all the ordered pairs on this graph and shift them down 4 units. So if we were to graph this particular function, we'd start with this parent function and we just shift that whole graph down 4 units. Copy the shape, just shift it down 4 units. Okay, so add on to the function, shift it up, subtract from the function, shift it down. Now, if we're adding or subtracting directly onto x, not onto the function itself, but inside the parent function, directly onto the variable, that's going to be a horizontal shift. So the second function we saw, notice we have the subtraction, but it's subtracted directly from the variable, directly from x. That's going to be a horizontal shift. Now, here's where we have something that's a little bit counterintuitive. It makes sense that if we add on k units to y, then it's going to shift us up. We subtract from y, well, that's going to shift us down. It makes sense. It's actually kind of flipped when we're talking about a horizontal shift. So that's going to be left and right, okay? If we're adding on, then intuition says we're adding on to x, so we're going to shift everything to the right. That's what your intuition would say. It's actually going to be the opposite. So if we take x and we're adding on a number directly to our x, intuition says we're going to the right. It's actually the opposite. We actually go that many units to the left. And then in the same way, if we're subtracting directly from x, intuition says, well, that's going to go in the negative direction. It's the opposite. It's going to flip and it's going to go to the right. So I always remember this as x lies. Whatever operation is done directly to x, you do the operation that's sort of contradictory. You do whatever seems not intuitive. You don't follow your intuition for that one. So for the horizontal shift specifically, you do opposite in terms of the direction. You do opposite of what the operation is telling you to do. So if we add, we go to the left. We subtract, we go to the right. So notice those are all the different ways that we could do a shift. We can shift up, we can shift down, we can shift left, we can shift right. We can do combinations of them. So we could shift up and we could shift to the left at the same time. If our function had both an addition outside the function and an addition inside the function added directly onto x, then we would have both of those transformations applied to our parent function. So not only can we shift, we can also stretch. So shifting is not going to change the shape of the graph. So if we were looking at the x squared graph, for instance, shifting is going to take the shape and it's just going to move it around on the coordinate plane. It's what we call a rigid transformation. Rigid transformations will not change the shape of the graph at all. They'll just change its position on the coordinate plane. Stretching and shrinking will give you a graph that has the same shape, but it's warped in the sense that it's either steeper maybe or it's wider, something like that. So we actually have two different types of stretching and shrinking. We can do it vertically, we can do it horizontally. We're just going to focus on vertical stretching and shrinking because that's going to cover pretty much all the situations we're going to need. So if adding and subtracting represents shifting, moving around on the coordinate plane but not changing the shape, multiplication is what's going to give us a stretch or a shrink. So if we're multiplying on the outside of the function, that gives us a vertical stretch or shrink. So notice the consistency between these two types of operations. We add or subtract on the outside, we multiply on the outside. That's what makes both of these types of transformations vertical. Once we move the operation inside, and we're doing it directly to the x, directly to the variable, that's what's going to make the transformation horizontal. So we're multiplying in either case. How do we know whether we're stretching or shrinking? First off, what do I mean by stretching or shrinking? Well, if you imagine the square function, a vertical stretch would be like grabbing the tails of the graph and pulling them upward, which would essentially have the effect of taking the U-shaped graph and making it a steeper U. So it's still going to be U-shaped, but that stretch is then going to make it a steeper, a skinnier U-shaped graph. A vertical shrink, another word for that is compression, would be like taking the tails and pressing them down vertically. So the effect of that would be take the U graph and it would widen the graph. So it would still be U-shaped again, but now it's a wider U versus that skinnier U. So how do you know which one you've got? How do you know whether you're stretching or shrinking? It's going to depend on what the value is of the number you're multiplying by. So we're only going to look at positive numbers. We're going to assume that the number we're multiplying by is positive. What if the number is actually negative? Well, we'll talk about that in just a minute. So assume it's a positive number. If the number we're multiplying by is greater than 1, now that doesn't mean it has to be a whole number. It could be 1.5, it could be 3.6, whatever we want. As long as it's greater than 1, we're going to stretch away from the x-axis. So say for instance it was a 2. What's really happening? What's happening is we're taking the y values and we're multiplying all the y values by 2. Another word for that is we're doubling. We're taking the y values and we're doubling. So visually what that's going to look like is that we stretched the graph. We took the tails of the graph, we stretched them away from the x-axis, we doubled the distance between the x-axis and our particular points. Now again, we said the number has to be positive, so either it's greater than 1, or if it's still a positive number but it doesn't fall under this case, it has to be between 0 and 1. It can't be 0, because if we multiply by 0, well, nothing happens. If we multiply by 1, well, nothing happens. If you multiply by 0, the whole thing goes away. If you multiply by 1, you're not really changing anything. But if it's a number between 0 and 1, something like 1/2 or 1/3, 1/4, something like that, that's going to be a shrink. So we're shrinking the distance. If we were to take all of the y values and multiply them by 1/2, then we're now cutting the vertical distance in half. We're shrinking how far away our points are in terms of their relation to the x-axis. So that's going to be our vertical stretching, vertical shrinking. We get that from multiplying by something other than 1. Now we said the numbers have to be positive. Why do they have to be positive? Well, the negative, if there's a negative, it means there's something else going on. So if we have a negative multiplied by our function, that is actually going to be a reflection. That's flipping the graph. This is another rigid transformation. It's not changing the shape, it's just changing the orientation. If we multiply the whole function by a negative, that's going to reflect our graph over the x-axis. In other words, anything above flips so that it's below, and then anything that started below the x-axis flips so that it's above. So just to show you how you'd handle these two cases in tandem. If you were to look at the third example on that first page, we had negative 4x squared. Okay, so we've got the x squared, it's a variation of this graph. Although there's only one number in front of the x squared, there's actually two transformations being applied here. You have to think of the negative and the 4 as being separate components representing separate transformations. So we're multiplying by a 4, and then we're also multiplying by a negative 1. So multiplying by the 4, we're multiplying something greater than 1. That's going to take our x squared graph and it's going to stretch it vertically. So multiplying by the 4 is going to take the tails of this graph and it's going to stretch them vertically by a factor of 4. It's going to take that U-shaped graph, it's going to make a steeper U. The negative is separate from the 4. So the negative multiplied out front is going to give us a reflection. We're going to reflect over the x-axis. So we're going to take that stretched graph and we're going to take it and flip it across the x-axis. So all the points above are going to flip so that they're equally distant below. What do I mean by that? Well, think of flipping the distance. So if we were 4 units above, now we flip it and we're 4 units below, something like that. So anytime you see multiplication and you're multiplying by something that's a negative number, something like -4, -1/2, anything like that, the negative means one thing and then the number itself means another thing. So you have to treat those as two different transformations. So we actually have all 4 different categories represented in these 3 functions. This function has a vertical shift, this function has a horizontal shift, and then this function has a vertical stretch, and it also has a reflection. So what if we were to put all of those together? Well, that certainly could happen. If we were to put all of those together, then that means we then have a graph that has all of those different kinds of transformations. It's not ultimately going to matter what order we apply these transformations in. If we were to add on some additional transformations other than the ones we're covering here, order is going to matter. But in our situation, we can pretty much apply things in any order and it's not going to be too big of a deal. So let's look at a basic example of what this is going to look like. Now, rather than looking at the actual parent functions and doing actual variations of those elementary graphs, let's just look at a little basic snippet type graph. We want to apply transformations to this particular graph. So this is our function. This is all it is. It stops between -4 and 5. So we don't have any more graph out on the tails. This is all we've got. So based on this being the graph of our function, we want to determine what each of these transformations would look like for our function. So our first new graph is going to take our original function and we're going to subtract 3 from it. So let's go to the list. What are we doing? We're taking our function and then we're subtracting a number from the function as a whole. So what that's going to do is it's going to take the original graph and it's going to shift that graph down by that many units. So starting with our original graph, which I've also copied over here on the next page or on the next coordinate plane, -3 off of our original function tells us to take that original graph and shift the entire thing down 3 units. So how do you do this if you're not a super visual person? We'll do it step by step. Identify the key ordered pairs that you have. So we have -4, -1, -1, 2, let's see, 1, 2, 3, -2, and then 5, 0. If we can apply the transformation to just those points, then it's essentially just a matter of connecting the dots. That's the whole idea behind the graph is going to have the same shape. It's the same shape, it's just a different location on the coordinate plane. So one by one, we can take those individual points, in this case 4 of them, and just move them down 3 units based on that transformation. So move this point down 1, 2, 3 units, down 1, 2, 3, and then so on and so forth for the other 2 graphs. And then we just connect them based on the shape we already know that this graph has based on the shape of this parent function. So although this isn't one of those elementary functions we looked at the beginning, this is the parent function for all of these different function transformations. So that would be our final graph in this case. Same shape, just shifted down 3 units. Now, what if instead we have a function and we're adding a number inside parentheses? In other words, we're adding directly onto x. This is a different kind of transformation. Anything done directly to x is going to be horizontal. So in this case, we're taking x and we're adding on a number. Remember, this transformation, the horizontal shift, is kind of counterintuitive. What your intuition says, it actually does the opposite. So if we're adding on to x, that tells us we're shifting horizontally, but the addition tells us that we're going to the left. We're actually going in the negative direction, even though the operation is positive, it's an addition. So in this case, if we're taking our function and we're adding 2 directly onto x, that tells us to take this original graph and shift it 2 units to the left. So again, we can go point by point, start with each of the individual points, and then shift those individual points 2 units to the left, one at a time, and then connect your dots. So same shape, just shifted 2 units to the left. Now doing the stretches, doing the shrinking, that's where it gets a little bit more complicated. So we really have to think about what the definition of a stretch or a shrink means. So 1/2 times f of x. Okay, so let's identify the transformation first. We're multiplying by a positive number outside our function, so that tells us it's a vertical stretch or shrink. The number we're multiplying by in this case is 1/2, which means we fall under this category. We're multiplying by a number, and that number is between 0 and 1. So if this is the case, we're going to shrink our graph's distance from the x-axis. Now, here's where we're going to have to be really careful about the actual points. What does shrinking the distance mean? I want you to look at the original graph. Let's just start with the original one. I want to go point by point, and I want to look at how far each of these points is away from the x-axis. Okay, so this first point is below. Notice it's 1 unit below. So its distance from the x-axis is 1 unit, and that's 1 unit below. Okay, this next point is above, and it's 2 units above. So its distance is 2 units, and it's 2 units above. This one is 2 units below. And then notice this point, this one is actually on the x-axis. So if we were to define its distance away from the x-axis, well, if it's on the x-axis, its distance is 0. So what we're doing when we multiply by something like 1/2 is we're taking each of those vertical distances, in this case it was 1, here it was 2, then 0, and we're multiplying each of those distances by 1/2. We're cutting the distance in half in this case. So our first point was 1 unit below. If we cut that distance in half, then it's going to be 1/2 unit below. Now notice that's going to take you off of the grid. That's okay. In a lot of situations with graphing, you are going to have to go off the grid. You're just going to ballpark it. Just do your best, okay? So we take that distance of 1 unit, cut it in half, so now it's 1/2 unit below. Now this next one was 2 units above. If we cut that distance in half, then 2 units cut in half is going to be 1 unit above, okay? This next one was 2 units below, cut the distance in half, and it's going to be 1 unit below. And then what about the last one? It's on the x-axis, so we determined its vertical distance from the x-axis is 0. If we cut 0 in half, what do we get? Or just think of it more literally as take that vertical component, take 0, and then multiply it by 1/2. Well, 0 times 1/2 is still 0, which means that that last point doesn't actually go anywhere. If we're stretching or shrinking in relation to the x-axis, think of things on the x-axis as being fixed. Those points aren't moving. What's moving is everything that's then above or below the x-axis. We're changing those distances to the x-axis. But if we're already there, well, we can't get any closer or further away if we're already there. So that particular point is stationary. It's not going to go anywhere. So we connect our dots based on those points that came from cutting the distance, the vertical distance, in half. And notice again, it's going to be a graph of the same shape, but it is in fact warped. It's got the same general shape in terms of what's happening as we go from point to point, but if you were to imagine taking this graph and shrinking it vertically, imagine pressing each of those points so that they're then closer to the x-axis, this would then be the graph that we end up with. Now, what if instead we multiply by 2? So same location, same operation, but now we're multiplying by something greater than 1. So if we're multiplying by something that's greater than 1, that's going to stretch our distance away from the x-axis. So rather than cutting our distance in half, now we're taking all of those same distances and we're doubling them. We're multiplying them by 2. Ultimately, you don't have to think of it as doubling or cutting in half. Think of just taking the y values and multiplying by whatever that number is. What if it's 1/3 or 1/8 or 15, something like that? You don't have to worry so much about this is cutting in half, this is doubling. Just take all of your y values and just multiply by whatever that value is going to be. Once you multiply by that number, that's going to give you the new y coordinates for all of your points. So the x coordinates are going to stay the same. The y coordinates will be reflected by whatever you get when you multiply. So in this case, this y coordinate was -1. We multiply that by 2, and we get a -2. Or again, think of that as doubling the distance. So this was 1 unit below, we double its distance, well that's going to be 2 units below. Now the next one was 2 units above, so multiply that by 2, we get 4. Or think of doubling the distance, so 2 units above, we double that, and that's going to be 4 units above. This is 2 units below, so 4 units below. And then again, that point that's on the x-axis, how far away is it from the x-axis? Well, it's there, so it's 0 units away. 2 times 0 is still going to be 0. We double the distance of 0. Well, 0 doubled is still 0. So that point's not going anywhere. So now again, we connect those new dots, and that's going to be our graph. So again, same general shape in terms of how the points connect to one another, but now imagine taking this and stretching it vertically. So imagine taking this point, stretching it, stretching this one down, stretching this one down, and then of course this one is fixed. So it's like the point we're pulling off of in a sense. And this is going to be the actual graph we get. Okay, let's look at one more. What's the transformation we haven't done? I don't think we've done a reflection. So anytime we take our function, multiply by a negative out front, that is going to reflect the graph. So anything that's above will flip and go below. Anything that's below is going to flip and go above. Okay, so let's make sure we know which one is which since I have both graphs here. Our original graph starts below, goes above, then below, and then onto the x-axis. So if you were to imagine taking each of these points and reflecting them, again, if you want to go back to the distances, that might be helpful. So this particular point was 1 unit below. If we reflect this graph, then that point will reflect so that it's then 1 unit above the x-axis. This point was 2 units above, we reflect it, it's 2 units below. 2 units below reflects 2 units above. Now again, what about that last point, the one that's on the x-axis? If we reflect it across the x-axis, what's happening? Well, it's reflecting across itself, but you don't actually see any measurable change based on doing a transformation to something that's on that axis. We flip it above to below, you don't actually see the change because 0 units above, 0 units below, well, it looks the same. You can't actually see a difference in those two. So that last point, again, nothing happens to that one. So below to above, above to below, below to above, and then this one stays where it is. So again, notice for this one, the shape didn't change. What changed was the orientation. So negative versus positive, we call that the orientation of the graph. For things like our actual parent functions, we can think of an upward or a downward orientation, particularly for something like absolute value or x squared. They very much have an orientation in terms of where the arrows are pointing. If you have a graph that is infinite, that does continue, that does have arrows on its tails, then what you're changing is the orientation of the arrows. Anything pointing up then flips to point down. Anything pointing down then flips to point upward. So let's put it all together. So we've looked at the transformations, we looked at those basic parent graphs, the elementary functions. Again, I strongly advise you spend some more time with those. Make sure you understand where the ordered pairs come from. Graph them in your graphing calculator if need be. Do the ordered pairs by hand if you want, but make sure you have an understanding of why those graphs are shaped the way they are just based on the types of functions you have. So when we want to graph transformations for those, there's 2 layers to what we need to do. So number 1, we have to look at that function and we have to know where did it start from? What's the parent function? What's the elementary graph? In other words, what's the shape that we expect to see for this particular function when we graph it? And then also we have to identify our transformations. How do you know what represents a transformation? Well, anytime you see a constant number added, subtracted, or multiplied somewhere in your function, you know that represents a transformation. So the actual operations that represent the function, the parent function, are going to be the other types of things. If we see an exponent, if we see a radical, if we see the absolute value, something like that, those particular operations represent those function categories, the parent functions. The other types of things, anytime you see something with a fixed number that's then being tacked on to one of those parent functions, that's going to represent a transformation. So let's look at a few. So here's our first one. Y is equal to the absolute value of x plus 1 minus 3. Okay, so let's start with the parent function. Imagine dropping off anything added, subtracted, or multiplied here. What would still be there? Well, we'd get rid of the plus 1, that wouldn't be there. We'd get rid of the minus 3, that wouldn't be there. That's all the addition, subtraction, and multiplication. What remains is that absolute value. So that means our elementary function, our parent function that we're working off of, is going to be f of x is equal to the absolute value of x. So we know that this function, the one we're actually graphing, is going to have the same shape as this function. And for now, while we're still learning these functions, you're going to go back to your list and you want to verify what that graph looks like. So our parent function is the absolute value function. It's going to be this one. So this is going to be the basic graph we're working off of. Now, not only do you want to understand the shape, but it's also helpful to have a sense of where these ordered pairs are. These key 5 ordered pairs, these points graphed in the middle, knowing where those are and being able to graph them accurately is going to be helpful as you actually put the transformations into practice and actually put them on your graph. So not only do we want the V, but we also want those specific ordered pairs that we're starting with. So while we're working on graphing transformations, I want you to graph the parent function as your starting point on your coordinate plane. It's what you're working off of. So having that visually on your coordinate plane is going to make graphing the transformations a little bit easier, rather than just having to start from scratch and determine where your actual points are going to go. So we've got our V-shaped graph, and then we have our 5 ordered pairs. So 0, 0, 1, 1, 2, 2, and then -1, 1, and -2, 2. So notice I graphed that in a lighter shade in this case. That's going to be our parent function. So our transformations are then built off of that function and off of that function's graph. We need to identify what they are though. So we have an addition of 1 and we have a subtraction of 3. That tells us we have 2 transformations in this case. So let's start with the addition of 1. We need to pay attention not only to the operation, to the fact that it's an addition, but we also need to pay attention to its location. So you'll notice that this 1 is added inside of the absolute value. Notice it's added directly onto x, whereas the 3 is outside of the absolute value, so it's not directly attached to x. So for the plus 1, it's inside of the parent function, and it's a number being added. So it's inside of the parent function and it's a number being added. So that tells us that it's going to be a shift to the left. So that plus 1 would take this parent function and would shift it 1 unit to the left. So that is going to be our first transformation, to take that parent function, shift everything 1 unit to the left. Now the -3, notice that is outside of the parent function. So the subtraction means one thing, the location means another thing. So we're subtracting outside of our parent function. So this is going to be what it looks like generally. That means we're going to shift down. So we're going to shift everything from where it currently is down 3 units. So that's going to be our second transformation. So the graph of this function is going to start with the graph of the elementary function, which is going to be this pretty V-shaped graph, but it's the variation where we shifted everything left 1 unit and then down 3 units. So with something like this, you may be able to do both transformations at one time. What you want to do is go point by point and apply each of those transformations 1 point at a time. It doesn't matter which point you start with. If you want to start on the left, work your way to the right, that's fine. If you want to start in the center and then go left and right separately, that's fine. Try maybe a couple things and find what seems to work well for you, and then just stick with it, get into a pattern. So I'm going to start on the left. So we have a point at -2, 2, that's the point on our parent function. We want to go 1 unit to the left and then 3 units down. So 1 unit to the left, and then down 1, 2, 3 units. So the new coordinates for that point after we transform it are going to be -3 and then -1. Okay, our next point at -1, 1 unit to the left, and then 1, 2, 3 units down. Okay, the next point, the one that's at the origin, 1 unit to the left, and then 1, 2, 3 units down. Now, once we've gotten those 3 points, we can actually use the symmetry of this graph in order to get the rest of them without having to mechanically go through and find the new coordinates. If you recognize the shape, the general shape of the absolute value graph, you'll notice that there is horizontal symmetry. So everything to the left of that central point is matched by everything to the right. So if we then just take mirror images across that new central point, that's going to give us the other ordered pairs we want to graph. And then of course we just connect the dots, keeping in mind that if our parent function is a V-shaped graph, then the graph of our actual function is also going to be a V-shaped graph. So what are you actually graphing? What are you actually graphing when you're graphing the transformation? You're just really graphing the final function. So keep in mind, this function, the lighter one, the parent graph, it isn't really there. It's a guideline. It's something for you to work off of. But in terms of what your actual answer is, the actual graph for your function is just the one that resulted after you applied those transformations. So if you want to put the parent graph on your coordinate plane, I'd certainly encourage you to do so, particularly while you're practicing and you're learning how to do this. But keep in mind, you need to clearly indicate which graph is a parent graph and which graph is the actual graph of your function that you're interested in. So I did them in 2 different colors. Another thing that a lot of people do is maybe graph the parent function in a dotted line and then graph the actual function as a solid line. You can do colors, you can do that. Or worst case, you just label them. Maybe label this as absolute value of x, label this one as the actual function being graphed. Something though, you need to have something to differentiate if you're going to have both graphs on there, something to differentiate one function from the other. Now, I also want to show you how you can verify your graph in the graphing calculator. I do not want you to become dependent on the graphing calculator, particularly for graphing. You can't really learn to graph just using the graphing calculator. One issue with becoming dependent on the graphing calculator is if you mistype something and you don't realize it, if you become dependent on the graphing calculator, you're unlikely to catch your own mistakes. Because if you're just relying on it to do the work for you, you won't get to the point where you have a sense of whether or not your answers actually make sense, whether they actually fit the context of the problem. So you need to be able to see something like this, identify its shape, understand the transformations. You can use the calculator as a tool to help you get more accurate points. That's a great way to use it. But these kinds of things you need to be able to identify just by looking at the function without the use of the graphing calculator. But let's say we do want to graph this function, if nothing else, to verify that we graphed it correctly. So I'm going to go into y equals. If you have something there, clear it. And we're going to type in this particular function. So remember, the absolute value is going to be under math. So go to math, go to the number submenu, and the first option is ABS. So select that, hit enter. Now again, yours may just say ABS with parentheses, or it may format actual bars. Either way, it's graphing absolute value. Now we need to differentiate between what's inside and what's outside. So inside the bars, we have x plus 1. Now notice the -3 is outside, so I can't just keep typing -3. I need to tab over and get out of the bars. If your ABS just wrote ABS and put parentheses, you need to close your parentheses once you finish with everything that's inside of the absolute value. Otherwise, it's just going to keep typing inside the bars, which is not actually what you want to do. So tab over on the outside or close your parentheses and then -3. So let's look at the graph first. And again, I'm still in Zoom Square, so this is about as accurate as it's going to get. And if we compare it to what we have, notice it's a V and it's shifted over to the left and it's shifted down. Now that semi verifies things, But a great way to make sure that we really did graph it accurately is to verify the coordinates of these ordered pairs using the table. So second and graph is going to give us our table. We are saying, supposedly based on the transformations, we have a point at -3, -1. That should be on the table. Well, here's -3, -1, so that one checks out. -2, -2, so -2, -2, that checks out. -1, -3 became our new central point, so -1, -3, that's there. 0, -2, 0, -2, and then 1, -1. That one's there as well. So that's not a complete guarantee, but if we can verify that we have the right shape and we have several ordered pairs in common with our actual graphed one that we did, then that's going to be a pretty good confirmation that our graph is accurate. Okay, let's look at a couple more. So y is equal to -2x squared. So start with your parent function. Again, imagine removing any addition, subtraction, or multiplication from this function. What would be left? Well, the only thing here is a multiplication. We're multiplying by -2. So if you imagine pulling that off, you're left with x squared. That means the elementary function you're working off of is the squared function, x squared. We've seen this one a couple times. So remember, this is going to be a U-shaped graph centered at the origin. And we have some specific ordered pairs to work off of. So 0, 0, 1, 1, and -1, 1, and then 2, 4, and -2, 4. So just like the absolute value function has some symmetry, this graph has some symmetry as well, and you should use it to your benefit. So if you can graph everything to the right, just remember you have points that are mirror image to the left of that central point, what we call the vertex. So this lighter graph, that's our parent function. That's what we're starting off of. That's what we're applying our transformations to. So now we go back to the actual function. We have a -2 that's being multiplied out front. So what does that represent? Well, again, you need to be careful here. It's one number. -2 is one number being multiplied by x squared. But when the number being multiplied is a negative number, it actually represents two transformations. So remember, the negative means one thing, the 2 means something else. So we have to be careful here, and we have to make sure that both of those are considered independently. 2 is one thing, negative is another thing. So let's start with the negative. Let's just work left to right. So if we take our parent function and multiply by a negative, that tells us we're reflecting over the x-axis. So above to below, below to above. So that's going to be our first transformation. We're going to take the graph, we're going to reflect it over the x-axis. Now what about the 2? We're also multiplying by a 2. Forget about the negative, we've taken care of that. Now we have that 2. So anytime we multiply our whole function by a number, that's a vertical stretch or shrink, the number we're multiplying by is greater than 1. Now remember, it's technically less than 1, it's less than 0 because it's negative, but we're not treating the negative as being part of the number at this point, so we're just looking at the 2. So 2 is greater than 1, so that means we're going to stretch our distance away from the x-axis by a factor of 2, so a vertical stretch by 2. Now the order you do these in is really up to you. I personally would recommend maybe just doing the stretch and then doing the reflection. But again, it's up to you what you want to do. Okay, so I'm going to sort of go through it with stretch and then reflection, but either order, it's going to be the same. So let's start with the stretch. Start at the center in this case. So 0, 0, that's our original starting point there in the middle of our parabola. If we're going to stretch it vertically by a factor of 2, remember we're taking the distance between our point and the x-axis and we're stretching it by 2, we're doubling it. Well, this particular point is 0 units away from the x-axis. So if we double a distance of 0, we still have 0, right? So that one's not going to move when we stretch. Now let's work to the left. So this point is 1 unit above the x-axis. If we double its distance away from the x-axis, 1 unit above will become 2 units above. And then same thing for this point on the other side. All of the symmetric elements from the original graph are going to be handled symmetrically when we apply these transformations. So this point will also be 2 units above. Now these 2 points were both 4 units above. So if we stretch by 2, double their distances, now they're going to be double that distance. They're going to be 8 units above. So this point doesn't move. These points are now 2 units above. These points are now 8 units above. Now we're not quite done. That's our stretch. Now we have to reflect. So we're taking those stretched points and we're flipping them across the x-axis. Now that point in the center, what happens with the point in the center? Well, if we're reflecting it across the axis and it's already on there, it reflects, but you don't actually see a change. You don't actually see any measurable change. It just stays where it is, fixed on the x-axis. The other points do in fact flip though. So remember, 2 units above, 8 units above. If we reflect, those are now going to be 2 units below, and these will be 8 units below from where they originally were. So I want you to notice the x values are not changing. In terms of the x values for the coordinates we actually graphed, we've stretched the y values, but they're still along the same x value. That hasn't changed. All that's changing is how far away these points are, and then whether or not they're above or below the axis. But this is going to be our final graph. Again, make sure you differentiate between the two, graph them in different colors, maybe do the parent function as a dotted line, or just label the actual function you have. Okay, let's look at one final example. Let's put several things together. Now I've thrown this one in a particular order so we can talk about things like ordering and how you interpret what you're looking at based on maybe a non-traditional ordering of terms. So our function is going to be 2 minus the square root of x plus 3. Okay, so let's start with our parent function. What's going on here? If we were to take away all the addition, subtraction, multiplication, anything like that, what are we left with? Well, the 2 would go away, that minus would go away, the plus 3 would go away. We'd still have a square root. So that means our elementary parent function is going to be the square root of x. There's our square root function. We can verify that from the list. Here's the list. Okay, there's our square root function. So to get some points to graph accurately, we have 0, 0, 1, 1, 4, 2, and then 9, 3. Those are going to be our starting points, and that's going to be our shape. So we know once we graph this final function, it's going to have the same shape. It may be stretched, it may be shrunk, it may be oriented or shifted around, but it's going to basically be the same shape. So now that we've got that, we need to identify our transformations. Now here's where we're going to have to be careful. The transformations are not really listed in the order we normally see them in. So for instance, this 2 out front, what's going on with that? Well, technically, this 2 is a positive number. It's not being multiplied. For sure, it's not multiplied by the square root. It's not multiplied by x, but it's a positive number. So it may not immediately seem like it because it's 2 minus, so you might think it's being subtracted. What we have to focus on is the sign of the 2 itself. The 2 is a positive number, so 2 is actually being added on to the function. So what we normally would see would be something like this. What's happened is instead of adding it on after the parent function, we've added it on before the parent function. But what about the negative? If it's a subtraction right here, which it is, if it's a subtraction right here, how do we take care of that? Because this is positive, it's being added, but there's a subtraction. What's going on there? Well, the subtraction, you can think of the subtraction as being a negative multiplied by that square root part, multiplied by the radical. So perhaps a better way to write this so that it's a little bit more intuitive and it's easier to actually identify those transformations is to take that 2, again, notice that it's positive, so it's technically added, move it behind the parent function so that it looks more like what we're used to seeing, where it's attached after the parent function. So it's added on at the end, again, because it's positive, it's being added, But we still have to take into account that there was a subtraction here. The subtraction turns into a negative just multiplied by the radical. So this is probably the preferable way to write this expression so that we can easily identify what our transformations are based on how they're listed in the table. So we can now see there are 3 transformations. We're multiplying by a negative, we're adding inside the parent function directly onto x, and then we're adding onto the parent function at the end. So 1, 2, 3 transformations off of this elementary function f of x is equal to the square root of x. So let's start with that negative out front. Now before, remember, it was a subtraction, but at this point it's now just multiplying that square root by a negative, and we turned that 2, that positive 2, into a plus 2 at the end. So we're multiplying a negative onto our parent function. So that's going to take our graph, it's going to reflect it over the x-axis. So that's going to be our first transformation. Now the next thing we're doing, we're adding 3 inside the square root, inside the parent function. So adding inside the parent function directly onto our variable x is going to shift our graph to the left that many units. So remember, it's intuitively, horizontally, you add on, you think you're going to the right, you always do the opposite, x lies, so it's going to take you to the left that many units. So we're shifting left 3 units. And then plus 2 onto the parent function as a whole. It's outside the parent function, and we're adding. So that's going to shift our graph up that many units. So reflected across the x-axis, 3 units to the left, and then 2 units upward. Now, I did mention a moment ago, order doesn't really matter. Order may matter in this case. So how do you know what order to apply these transformations in? Well, let's think through kind of order of operations in this case. The order of operations is actually going to tell us what the strict ordering would be for graphing as well. So I want you to imagine for a moment, picture the function like this. Imagine for a moment that you were going to plug in a number for x. It can be whatever you want. Say you were just going to plug in a 0, doesn't matter. I want you to think about the order in which you would simplify everything down if you plugged something in like a 0 or a 1. Let's just say 1 so I can actually simplify things a little easier. So the first thing you would do would be to add a 3. You would simplify everything under the radical. So 1 plus 3, that would give you a 4. Okay, you take the square root, which represents our parent function. You would then multiply by the negative, and then the very last thing you would do would be to add the 2. That would be the strict ordering that order of operations would tell you to simplify something in if you were to plug in a number and then evaluate this function with that input. The order we follow in order of operations is also the order that we would follow, technically speaking, when we're going to apply our transformations. The reason the order is going to matter here is because of these 2 vertical transformations. If we reflect and then shift versus shifting and then reflecting, it's actually going to give us 2 different graphs. So the ordering we're going to have to follow is going to be the ordering that comes from following order of operations. So that's going to be the shift left, then the reflection, and then the shift up, because that's the order we would apply each of those operations in if we were going to follow order of operations. So if you ever have a collection of operations represented, a collection of transformations, and you're not sure what order to do them in, you're not sure if it matters, this is the way you can determine the order you would do them in. So imagine plugging in a value for x, follow through order of operations, determine the order you'd simplify all of those operations in, and that's going to tell you the order you'd have to follow for the corresponding transformations. So left, then reflect it, then shift up. Okay, so shift to the left, we have a point at 0, 0. Let's just look at 1 or 2 points, and then we'll look at this in the graphing calculator. And I want to show you something else you can do with the graphing calculator. So shift it to the left, 3 units. So 1, 2, 3 units, that takes it to -3. Okay, we're going to reflect it next. Now this one doesn't actually reflect, right? It's not actually going to go anywhere. It's on the x-axis. We reflect it over x. It doesn't go anywhere. But we then shift up 2 units. So up 1, up 2. And that's going to be the new location of what was originally at 0, 0. Now what about the point at 1, 1? Same sequence of transformations. So shift it left, 1, 2, 3 units. Reflect it vertically, and then shift it up 2 units. Now that one's kind of weird in the sense that we shift it and then reflect it and then shift it. It actually ends up right where it was before the reflection. That just happens because of the points we actually have here. But if we were to do the same thing with 4, 2, that's not going to happen. So shift it 1, 2, 3 units, reflect it. Now this one is 2 units above, so when we reflect it, it's 2 units below, and then shift it up 1, 2 units, and that's going to be the new location. And if we kept going, we can get as many points as we need just following those transformations. So that is going to be our final graph in that case. Now, just for the sake of verifying this in a little bit more detail on the graphing calculator, I want to show you how you can sort of build the transformations into a function, how you can really analyze what's going on one transformation at a time. Because we can certainly type this whole function in and get the final answer, that's fine. But another thing that's useful to do, at least maybe once or twice, is to take the function and kind of build on transformations to demonstrate how the function is changing one transformation at a time. Because technically, if we were to take, for instance, this graph and only apply one transformation at a time, we'd have a bunch of intermediate graphs, and the very final graph we'd get after we apply the last transformation would be the actual graph for our answer. So it's potentially helpful just to understand transformations a little bit better to see how one builds on the other in the particular order we have to follow. So let's do that with this one. I want to build on the parent function. So let's start by just graphing the parent function. So second and x squared gives us the square root, and then it's the square root of x. So that is our parent function. Let's just start by graphing that. Okay, and I'm still in zoom square. You might want to get in zoom square just so the transformations look a little bit cleaner. Okay, so that's our zoom square. We have our table. Okay, remember we still have those errors for the negative inputs because we can't plug in a negative number to a square root. It just doesn't work. So it starts at 0 and then it goes from there. Okay, now from that, I want to build on one transformation at a time. So the first transformation we graphed was the horizontal shift, which we got from taking x and adding on 3. So I'm going to go back to y equals. I don't want to clear this one. I'm going to leave the parent function there, but I want to add on another graph, specifically the graph we get after the horizontal shift. So I'm going to hit enter. Takes me down to another one, and I'm going to type this next one. But I just want the graph I'd get from adding on that horizontal shift, just one transformation at a time. So rather than the whole function, I just want to add on the square root of x plus 3. So square root of x plus 3 inside the radical, and hit enter. Okay, when I pop back over to graph, it's probably still going to have the square root on there, and then the next one it graphs will be the transformed one. So I'm going to hit graph again, still has that, and then notice it graphs another one to go with it. The one in blue versus the one in red. The one in red, the new one, is the original graph, but it's shifted 3 units to the left. So it's not the final answer, but it's the most recent answer we get after we do one transformation. Now, if I were to go graph by graph, transformation by transformation, the next transformation I apply won't be applied to the parent function. It'll be applied to the most recent one I got as I added on a transformation. So let's go back to y equals. I want to build on one at a time. So let's now clear the original one we did. Let's clear that. But let's leave this second one. We want to now build on from this graph the next transformation. So we first shifted to the left, and then we did our vertical reflection. So if we wanted the next graph that applies the next transformation, it's not just going to be negative square root of x. It's going to take the function we already had from the transformation we applied, and it's going to build on that negative from that. So the next one we're going to want is going to be negative times the square root of x plus 3. So what does that function represent? Well, it represents our most recent one after that one transformation, but it's going to take that function and then it's going to add on that negative that's then going to give me the reflection. So when I hit graph again, I should have the one that was already graphed, and then the function it's going to add on is going to be the new one. Okay. So it actually did it in the opposite order. The reason it does it in the opposite order is because of the order we have them typed in. So it's going to graph them in order. So this is the graph we got from the shift. And then when we reflect it, notice it's reflected from the shifted graph. It's not reflected from the original position of the square root. It's reflected from the new position from that shifted square root graph. And so that's going to be our next graph. And then from the shifted and reflected graph, we then shift up 2 units. So if I go back into y equals, I no longer need this one. I've now built on the next transformation. So if I clear this one, I can then do my final graph. So negative square root of x plus 3, that has our shift and our reflection. And then to that we want to add on 2. Now don't forget, if you want to add 2 outside of the square root, then once you get out of the square root, you have to tab over in order to get out from underneath the radical. And in this one, it should graph it in order. So we're going to see the shifted reflected graph, and then we're going to see the result of shifting that up 2 units. So there's the shifted reflected graph, and that's the result we get after shifting it up 2 units. Okay. So to verify that we have the correct one, let's clear everything but the final graph. And that's going to be the graph we want. So there's our final graph. There's that final graph. Let's go and double check some points. So let's go into the table. So second and graph. Okay. So we have negative 3, 2. Well, there's negative 3, 2. We had negative 2, 1. We had 1, 0, so there's that. And if we've done the transformations to 9, 3, that now takes us to 6, negative 1, and there's 6, negative 1. And then of course we connect the dots following that particular shape. Now just in case you were wondering, you're looking at this and you're wondering, well, why do we have stuff over here? Isn't the square root supposed to stop at 0? The answer is yes, with a caveat. Notice we now no longer have just x under the square root. We now have x plus 3. So we can actually go a little bit further out in terms of our x values and not have a negative under the square root. If we were to let x be negative 3, then negative 3 plus 3 gives us 0. Square root of 0, we're still good there. If we went out further though, say we let x be negative 4, negative 4 plus 3 is going to give us negative 1. And then we try to take the square root of that and we have a problem. So those restrictions we have, particularly for something like the square root, they do apply, but the basic restrictions only apply to the parent function. Once we start to make changes to the parent function, the way the restrictions apply can also change. So yes, we do still have restrictions and we do still have limitations on the domain, on the x values. But because we now have a different value underneath our radical, what that looks like can actually change. We now can go a little bit more negative in terms of our x values before we run into something that makes our square root undefined. So that gives you a little taste of what graphing looks like. There are actually many more parent functions that we will potentially see. We're going to focus on these and we'll talk about other graphing techniques for other more complicated kinds of functions. But I want you to think about graphing from this context. Think of identifying your parent function. What category does your function fall under based on the kind of operations you see, what sort of other things are in the function in terms of addition, subtraction, multiplication. That's going to give you variations of your parent function. So rather than having to graph point by point every time, being able to generalize, be able to think more in terms of the category of functions, the types of changes we have, that's going to be a beneficial way to graph.